This is the last section in the unit. This is lesson 6.8, scatter plots and line of best fit. Goals for today are I can identify whether there is any correlation between variables using scatter plots. I can sketch a line of best fit for a data set that has been graphed. And I can write the line of best fit equation for a set of data and use it to predict future outcomes. All right. So correlations have one of three different forms that we're going to study. They're either linear. Notice the dots, a scatter plot that's been graphed here. Those dots roughly follow a straight line. So we would say that this particular graph here has a linear correlation. An exponential would follow a curve like this, going off into space, right? That's exponential. And then there's a U-shaped distribution. So we either have a downward facing U or an upward facing U. That would also be a correct correlation as well for U-shaped. All right. So you also have negative, positive, and no correlation or no direction. So for linear correlations, it's like slope. These have a negative correlation because their slope is running downward from left to right. This is a positive correlation because it's running upward from left to right. And then this is no direction at all because it doesn't face either up or, it doesn't decrease or increase. So it's simply horizontal. So no direction on the correlation there, okay? So strength of correlation. Well, the closer the dots are to the shape of a line, to the shape of an exponential curve, the shape of a U-shape, the stronger the correlation. So the more scattered they are, the more weak they are. So this is close to the line, but this is more scattered. Okay. So you've got one that's very strong. You can see the moderate. They're kind of, they're loosely in linear form, but they're very far away from the line. And then this is just a weak correlation. I can't even begin to draw a line that represents these dots because they're just so scattered. Okay? All right, look at, this is interesting. I wanted to show you one particular world application here. So this is a graph of health and income. So on the y-axis, we have the health of a nation, its life expectancy. We see that sick is low and healthy is high on the y-axis, right? And then if you look at income down here on the x-axis, poor is getting closer to the origin, and rich is getting further away from the origin. And so you can see some of these large populations like India has kind of a middle range of health and kind of in the middle of the income path. China is healthier than India and wealthier than India. And then you look at Japan, man, they're doing really well. They're very healthy and they're fairly wealthy. And the United States, not as healthy as Japan, but wealthier than. So, and you can look at some of these other ones, like there's Qatar right there. They've got a ton of oil. Here's the UAE, the United Arab Emirates. They got a bunch of oil. Here's Saudi Arabia. They got a bunch of oil. So you can see all these people with oil. They're doing very, very well. And then you've got these countries like Afghanistan down here in Somalia. Look at Somalia. I mean, they're a very poor nation, and they're very sick. They're not very healthy at all. So that's how you kind of read this as a scatter plot that shows there is a linear correlation here, isn't there? All right, so just to give you a good example of a real life scatter plot and how economics might use that, okay? So here, example one, you're going to make a scatter plot right now. So use the data below to create the given scatter plot, and then fill in the guided sentence below. So you're just going to plot these points, 6, 4, and 3, 8, and 2, 6, 5, 7, 7, 5, 1, 9, 4, 5, and 9, 2. So the scatter plot shows positive or negative association. Well, I would say that it looks like the values are going down as we go left to right, so that would be a negative association because the plotted values of x increase. As the values of x increase, the values of y generally decrease. So as x goes up, y is going down, and that gives us a negative correlation. Okay, so you give this one a try there. Stop the video and come back and check. Not too complex, are they? Kind of a nice way to end our semester. Doing something that's not quite as difficult as before. Maybe get a little more difficult as we go here. Can't promise. So, wow, this one, very similar to the last one. This got a negative correlation because the plotted values of x increase. As the plotted values of x increase, the values of y decrease. Okay. Oh, here's one. I don't think you need to try that one. I think we got to, well, let's do it anyway here. 6, 6. Maybe it's a positive correlation this time. We'll see. It's kind of starting that way. 7, 6. 2, 3. 9, 7. 6, yeah, 1, 3. So this looks like it's going positively. I mean, we don't have a choice of saying it's not because the values of y are increasing as x increases. So this is, I would say, this is kind of a moderate correlation, though. It's not a strong correlation because it's not very tightly packed around what would be like the line of best fit, but it's kind of moderate. Okay. All right. So describe the correlation in the scatter plot. The scatter plot shows: is it a positive linear? Is it a positive linear with one outlier? Well, what's an outlier? Well, an outlier is one of the dots that doesn't fit the pattern. So see that guy there, kind of off in space by himself. I mean, wouldn't it be nice if that wasn't even part of the set because it's not even close to the other dots? That's an outlier. All right. So this one definitely has an outlier, but is it positive linear with an outlier or negative linear? Negative linear with an outlier? Which one is it? Non-linear? No correlation? I think there's definitely a correlation here, and it is positive linear with one outlier is what this is, okay? Because as the plotted value of x increases, the value of y is generally increase, okay? All right. Give this one a try. Okay, do you see any outlier here? Yeah, I don't see an outlier. I think they're all pretty well bunched up around a straight line. And it's not positive. I think it is a negative linear correlation because the plotted values of x increase. As the values of x increase, the values of y generally decrease. Okay. Try this one. And this is like all over the page, right? I mean, the scatter plot shows it's not a linear at all. So it's not linear, it's not linear, it's not linear. I think it's non-linear. Actually, I think it's worse than that. I think it's no correlation. It's not even like an exponential or a U-shaped. It's just none. Because as the plotted values of x increase, the values of y generally follow, so they show no pattern, right? They don't show any pattern. If it had been like, that exponential or U-shape, we would see some kind of pattern to them. But there's just no pattern here at all, right? Okay. And they're all outliers. Everything's an outlier here because they're so scattered. All right. Line of best fit. Well, line of best fit is simply a straight line that shows the relationship between the data points on a graph. It's also known as a trend line or a line of regression. And so what you want to do with it is you draw a trend line so that you can show a trend between points or predict the behavior of data. You can show the relationship between the variables. You can make predictions. We can actually write an equation of our line of best fit and then use it really to do this one here, to show the relationship between the variables and then to make predictions. Okay, and we can predict behavior of the data. All those things come from that trend line. Okay, so graphing a line of best fit is just making sure that line goes through the middle of the data and kind of follows the slope of the data. So something like this for that one. This one I would kind of, I'm trying to have as many points above the line as below the line, but sometimes I can't do that. It's got to kind of go through the middle of the data. So this one's kind of tricky here. I don't know, like that maybe. Yeah, I think that's pretty good. And so they're going to grade you on these on Desmos, right? So and if you'll figure it out fairly quickly there how close you have to be, but I think those are good lines of best fit there. So let's plot some points. 6, 4. Make a scatter plot, and we're going to do our line of best fit for some data points that we plot. So 3, 6, 2, 3, 8, 2, 6, 5, 7, 7, 5, and then 1, 9, 4, 5, and 9, 2. So for that data, I'm going to kind of go, I'm going to start at 9 and just draw this straight down through here like this. Okay? And sometimes I'm just going to be real obvious about trying to go through some points at the ends there, like that, So I want to be able to identify a couple points on that line. That's what I'm trying to say, okay? So it says plot the points, which we did, draw the line of best fit, which we just did. Then it says write an equation, and that's the real key here. So if you do this correctly, you're going to give yourself an easy y-intercept, which I did. I gave myself a 9, so that's B. And then the slope, I just can't really tell. I don't go through any other corners exactly. You see that? You might. Yours might. Like you might go right through that point right there. So just feel free to use any points because our equations can be slightly different, all right? Understand that because our line's going to be different. We're not going to have the same exact slope to these things and maybe not even the same B value, okay? And so I'm just going to use this point here and this point here and count the slope. So it goes down 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my slope is -7 over 10. So my equation is y equals -7/10 x plus 9. So then it says, what will be the value of y when x is 15? So we're just going to plug 15 in there for x. So it's going to be -7/10 times 15 plus 9. So -7 times 15, right, is 105 divided by 10 is -10.5 plus 9. So I got an answer of -1.5. Okay? So if you think about it now, if this graph were to continue until we got out to 15 on the x-axis, we'd probably be below the x-axis at that point. I think it probably would cut through at some point. Let's look at this one. It says when y is 20, what's the value of x? Well, now they're telling us a y value. So y is 20 equals -7/10 x plus 9. So I have to subtract 9, and I'm going to get 11. And then to get rid of this fraction, I flip it over and multiply. So I go to -10 over 7. So -10 times 11 divided by 7 is -15.7. So, these don't work out nice and neat, and they're kind of nasty at times. Okay? So when y is 20 on my graph, X is like back here in the negatives, right? So interesting there, right? Okay, that's finding some values, predicting some values. We're going to put context to these here pretty quick. You guys try this one, see what you get. So I'm going to plot 6, 6, and 4, 4, and 3, 1, 7, 6, 2, 3, 9, 7, 8, 6, 1, 3. Well, it looks like we have an outlier here on this one. You see this guy? Looks like an outlier. The rest of them look like they're going right around this. I'm going to go right there. Okay. So I've given myself a good point here. I've given myself a good point right there. Yeah, I can't do much better than that. So the b value is going to be 2 for my equation. My slope is up 1, 2, 3, 4, 5 over 1, 2, 3, 4, 8, 9. So my slope is 5 over 9. So my equation is 5/9 x plus 2. And remember, your slope may be a little different than mine. Like maybe your slope is 1 over 2 because you go right through that point and that point, right? So maybe that's your slope. Okay, remember there can be varying answers, but they have to be close, right? So what will be the value of y when x is 15? Well, I'm going to take that 5/9 times 15 and add 2. So that's 5 times 15 divided by 9 and then add 2, and I get 10.3. Okay, so rounding that off to the nearest 10. So you're not going to get nice, neat answers. Remember that. You could. It's possible, but in most cases you're not. So what about when y is 20? That's equal to 5/9 x plus 2. Well, I'm going to subtract 2 and get 18. I'm going to multiply by 9/5. So that's 9 times 18 divided by 5. And I get 32.4. Oh, that came out to be an even decimal. Right? Okay. So if this line continued until we were at 20 on the y, we'd be all the way out at 32.4 on the x. Okay. All right, how about some context now? So Anne is trying to find the elasticity coefficient of a super ball. So she drops the ball from different heights and measures the maximum height of the ball after the bounce. And the table shows the data she collected. So we're going to do this as the initial, and then this is after the bounce. And we have to choose a good scale here on this, right? It says, all right, the table below shows the data she collected. Draw a scatter plot, find the equation. Okay, so let's see, on the x-axis, we got to go from 30 up to 70. So what should we start at there? Should we go by like tens? 10, 20, 30, 40, 50, 60, 70, or by fives? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. So yeah, that's not too bad. So we go 10, 20, 30, 40, 50, 40, 50, 60, here's 70. And then let's do the same over here. We're going to go, because we only need to go up to, the max is 52. So then we're going to go 10, 20, 30, 40, and then 50's in there somewhere. So 30 and 22, and 35 and 26, and 40 and 29, 45 and 34, 50 and 38, 55 and 40, 60 and 45, 65 and 50, and then 70 and 52. All right. So there's some good points in there. Like we went through all at the same time. Well, that doesn't look quite right. So I'll try this. I'm going to definitely go through this one, and then I'm going to go through like one back here. So maybe like this. There. That's going to be my line. Now, problem is I don't have a y-intercept here. So I'm going to need 2 points on the graph. So I'm going to use 2 points that my line seems to go directly through. So there's one. I believe that is this one, 65 and 50. That's point 1, so I'm going to use that one. And maybe this one right here. There's point 2, and that's 1, 2, 3. That's our fourth 1, 2, 3. That's our fourth data point right there. So let's use those two to figure out our slope. So change in y, I'm going to go from, or change in x, so 65 to 45, or 45 to 65 is a plus 20, and 34 to 50 is 44, that's a plus 16, right? Okay, so our slope then is 16 over 20, which reduces to 8/10, which reduces to 4/5. So there's slope. And then I can just use a point. I'll just use this point 65, 50. So our equation is going to be this. I'll call this one my x1 and my y1. Okay. So we got a slope. We got x1, y1. So point slope form looks like this. So y minus, I'm going to use 50. And slope is 4/5, and x minus 65. And now let's go ahead and write that in slope-intercept form. So we're going to go y minus 50 equals 4/5 x minus 4 times 65 divided by 5 is 52. And then I'll add 50. And I get -2. So there's my equation. So 4/5 x minus 2. What height would she have to drop the ball from for it to bounce 65 centimeters high? So notice we've got to keep going up before she would ever get a return bounce of 65. So that's a y value then. So let's plug that in for y. So 65 So you'd add 2, and that makes 67, and then you multiply by 5 over 4. So 67 times 5 divided 4. Tells me about 83.75. So about 84 centimeters on that one. Describe the slope and y-intercept in context. Well, the slope is how high it bounces per initial drop height. So it's actually bounce height per drop height. Bounce height per drop height. And then the y-intercept is -2, which doesn't make any sense in this problem. Means if you drop it from a height of 0, it's going to bounce to -2. And why isn't it 0, 0? Well, Yeah, that's a good question. It probably should be 0, 0. Okay, so maybe we should have put, yeah. It's because the recovery bounce, so if the initial height is 0, the bounce height should be 0 as well. So we could have started 0, 0 there. Okay? All right. So the assignment is going to cover all those things that you saw there.